World waits for no man.
Oh yeah, and also our classes are canceled on Wednesday because we have an assembly.
Okay, well, we'll have class. You just get the video and get to watch it. My intention is to, after we finish this one, to move over into three-dimensional quantum, which is the start of chapter 8. And that's going to probably, I will deal with the two-dimensional box. Your book deals with the three-dimensional box. It just adds one more level of complexity. But I will know you're not going to be there. I'll also send you guys out your homework, which I came up with for the next assignment. I'll send that out this afternoon. They're just going to be problems in your book, so I'm not going to type them up or anything. I'll just send them out. Do you have some idea when the person, the tech on your end, is going to get your room connected?
He just left to go talk to someone downstairs about it, so now we're just waiting.
Let me ask you a question. How far is it to a computer room?
Across the hall.
Well, that may be the quickest and best way until he gets your room connected. So, do you know how to get the TPC website?
Yes, sir.
Okay, so when you get the TPC website, when you click on the big state on the Tarleton website, if that's the way you get in it, then you can there's a live webcast out of College Station. So if you go under delivery modes, which it says, click that. It'll say live webcast. Click that, and you'll see channel 6, I believe, is our channel. I'll check that just a second. Yeah, channel 6 scheduled live webcast. And you click that, and it'll come up, and you can actually see what we're doing. And that way you can get something done and watch while they're waiting to fix your camera. Because I'm not sure how long it's going to take for them to get that camera fixed.
Okay, we're headed there now.
Okay, I'll give you a couple minutes and then we'll start. For you guys, basically the same thing I just got through telling them homework's due today. If you end up after 6 o'clock slipping under my door, I will be back after I go to the National Honor Society meeting and do my stuff down there this evening. So I'll probably be back by 6:30 or 7. No, we've got to be there at 6. 7:30 something, then I'll pick it up then. In terms of homework, we'll move on and deal with the homework of the next section. The main thing in Chapter 8 that we have to be concerned with is the hydrogen atom. The hydrogen atom involves some serious math. Plain and simple. Say whatever you want. By serious, I mean the following. First, it requires a differential equation, and it is 3 terms. So therefore, it requires a solution of 3 differential equations. The differential equations are not constant. They're not things you can write off your head. It requires separation of variable, and you have to be able to do that. It requires you to come up with the quantum numbers that require separation. That's where angular momentum, energy, and magnetism come out of. So that means you must be able to do that mathematics. When you're done with that, and you get the equations, which are non-trivial looking solutions of wave functions, you then have to be able to apply them, which means finding probabilities in 3 dimensions. Be able to find the operators, to find the angular momentums, and so forth. So you skip going step by step through that math. You will have trouble, because there's no way you can intuitively do this. So make sure that you're going to spend your time and work your way through it. It's going to take. Because it's so important, it takes time, we will spend some serious time there. So I expect that we'll be there all of next week, and possibly part of the week after that, all right, in chapters 8 and 9, because it is the coup de grace. With whatever time we have left after we get through with that, we'll move on and take on some other things. I plan to take on lasers and certainly nuclear, and probably a little bit of solid state physics since we have double E's in here. That will kind of finish out the course. But a big part of the second exam stuff is going to deal with handling 3-dimensional quantum systems. Why? We don't live in a one-dimensional world. We live in a three-dimensional world. Things like conservation of angular momentum do not appear in one-dimensional worlds. You don't have rotation in one dimension. It's a line. So all the discussions about angular momentum and that sort of stuff doesn't occur until you get three dimensions. You also don't get the idea of degeneracy, which is an important concept in one-dimensional quantum mechanics. So all the stuff we did in 1D was to get up to be able to do 3D. 3D is a big thing, so plan on it. And correspondingly, the mathematically. We get past the hydrogen atom, the math goes down. A lot of what you do in nuclear physics, at least as far as energy calculations and determining the amount of energy calculations, Q value, mass defect, basic ideas of how to build a laser and such, do not have much math at this level. Now, if you do a full quantum approach to the laser, that's a different story. But as far as just simple understanding of 4-level lasers versus 3-level lasers and so forth, that does not require the same level of mathematics. So certainly the most mathematical part of the course for sophomores is this upcoming part. You want to spend time. With that being said, let's pick up the quantum harmonic oscillator, talk about a little bit, and I sent you some stuff to look at. Drop down to what I have here. The most important thing in the quantum harmonic oscillator is A, to understand what we're trying to do, and B, to understand what you do when you hit a problem that doesn't have a nice, simple differential equation that you can just write the answer off your head. And often physics problems, most of the time physics problems don't have such nice things. It would be nice if, everything in physics was so simple in math that you needed 4-function math, but that wasn't the way the world works. You can either believe, like some theorists do, that that's because math actually creates the universe, if you would, that's the way the universe is, or you can think of it that math is a construct of the human mind, and our original question was how many wildebeest did you kill, or how many mammoths did you get, and so one mammoth and one mammoth was 2 mammoths, and that's what you're worried about, so you need differential equations to solve quantum mechanics. Maybe if we solve quantum first, you need advanced differential equations to work at Walmart, but you need 4-function mathematics to work quantum problems. I don't know. What I do know is we get tricky problems. And to do tricky problems, you got to be able to set them up. So one thing that I talked about last time is that you need to set the problem in a way that's stuff you can measure. So while the harmonic oscillator can be written as 1/2 kx squared for the potential, because I can't measure a spring potential, that's not a good way to do it. And furthermore, it's not only that, it's also because the real problem isn't really a harmonic oscillator. It's probably something that looks like this. It's this potential. But if I approximate that, because it's a continuous curve, it's some set of polynomials, if I don't go too far either side, I can represent that in this bottom area by this dashed line, which is a Hooke spring. And so I'm approximating it for small vibrations, for instance. Because if I let it do this other, then the math would get even harder. So we're often approximating things. And one of the things that we know well, we know a particle in a box. We know a free particle. We know a spring problem. We know a rigid rotator problem. And we know a central force problem. 5 problems in physics that you should know well. I told you that back in classical physics. In quantum mechanics, we're basically repeating those things. So the hydrogen atom is a central force problem. And the angular momentum solution will be the rigid rotator. And this is the spring. We've already done the particle in a box. And a free particle is a plane wave. So we are repeating those 5 fundamental projects that physicists know. Okay? Now, once I put this guy down, I modified him because back from classical physics, when we solved the differential equation, we found that, I told you last time, omega was the square root of k over n. And if you squared that, then you get omega squared is K over N. So what I want to do is I want to take and replace K with the frequency of vibration, because we've already found that when these things emit photons, they emit the photons that are related to the frequency by which the thing vibrates. And I want to replace it with the mass, because if I know the mass of an atom or if it's an electron, I know the mass. So those are things I can measure. So what he does is take this K, solve omega squared in terms of that K, so K is omega squared times M. Take that, substitute in for that K. When you do that, you get this. And so this is the potential that in advanced classes, solid state, quantum, and so forth, we think about saying, we don't say it's 1/2 kx squared. We say it's 1/2 the mass of the particle, the angular frequency squared times the position squared. But it's still 1/2 kx squared. We just write it in a different way. Now, we put that into the differential equation, as I told you last time. Let me back out. And my problem is this. This quantity in here, which represents the kinetic energy, is not a constant. It's a function of x. And there's no place that I can break it into constants. So I have to solve this differential equation, whose wave number, this whole big thing up here, is varying. It's not constant. And so I don't know the solution. So the way that we attack a problem like this is we see if we can use some symmetry or some good guesses, maybe. I mean, that's what people did years ago. They made some guesses, and if they made some guesses, they thought, you know, maybe they could get a rough feel of the function. So some things we know. If you were to go way, 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 way out and stretch the spring, you give the spring the little particle some energy and bounce back and forth, and it moves back and forth something like, you know, it goes like this, and it goes like this, and if it's classical, there'd be some maximum point it could stretch, and there'd be some maximum negative point it could stretch, and it would never be out here. And it would never be out here. Now, in quantum, never means unlikely in most cases. So the probability should be very low out here. And the probability should be very low out here. And in fact, we did that problem back a while back. We actually solved probability in terms of the time, and we built the classical probability interpretation. And you remember from the correspondence principle, quantum mechanics has to approach classical physics for high N. So I know one thing. I know that the probability should go off exponentially at the curves, the outsides. So maybe I don't know the answer to the problem, but I know some things about the problem. If I'm going to solve this problem, it needs to do this out here, and it needs to do this out here. And it's going to go up in the middle. Something else. What do you think about the probabilities here and here?
Probably the same.
Huh?
The same.
They should be the same. This thing should be even. The probability function should be even. Now this is the wave function. But when I square it to get probability, they got to be the same. So, do you think it'll be flat?
No.
No, I don't think it'll be flat. Now remember, classically, if a particle spends a lot of time, that is if it's moving slow, the probability of finding it should be high. And if it's moving fast, it won't spend much time there, the probability should be low. Where is it fastest at? Here, when it stretches the spring, or here, when the string is unstretched?
There.
In the middle.
In the middle. So if it's highest, it should have the low probability. That's one possibility. At least for large N, that's what you should expect. If you do that, classically, we did earlier, we got something that kind of looked like this. Draw that kind of in red. So that was the classical solution. That's not the quantum solution, but that's what our answer kind of has to go. It needs to go up on the edges, and it needs to stay kind of down in the middle. It had no probability of being out here. So that's classical. And I did that earlier in the course. Go back and look at that. I don't expect it to be constant here. I expect it to wiggle. So, I mean, I expect to see a bunch something, don't know exactly what, but maybe, something like this. And actually, these guys should, since this was a probability, these guys should kind of like this, my fault. Shouldn't go below the... So I expect it to have kind of a wiggle in the middle. I expect it to kind of fall off. The number of wiggles, well, that probably differs between different problems, just like it did in the particle in a box. But I do expect that the heights of these wiggles will not be the same. I expect the heights of the wiggles will go up near the end. Now, I haven't solved anything. I've just made some guesses, and the guesses could be wrong, but they're at least a chance. Now, to get these guys over here, I could do that if whatever my wave function had the following form. It looked like something in here, not sure what this is. And it had something that looked like that. Because if this was positive, then this would cause it to go down. And if this was negative and I square it, that would cause it to go down. And in the middle, this thing here, which I have no idea what it is what's causing it to wiggle up and down. When you square that, those wiggles will become the probabilities in here, and this will just make it go down even quicker. That does not mean that that's right, but it means it's a logical thing to start with. How do you know if it's right? If it meets the Schrodinger equation, it's right. So I can take this, and I can substitute in the Schrodinger equation, and I can see if it actually works. And the book and my notes show you a couple of cases. I did one where I put a constant in front, and it worked. And that's one of the states. I put another, I put an x term in front, and I put in the Schrodinger curve, and it works. And that happens to be the first. So really, if this always works, the real question is not this. I know how to get that and that. The question is how to get these. How do you get a set of polynomials in a differential equation that's not trivial? Well, the first thing is to stick these into the Schrodinger equation and change that from an equation trying to find the wave function to an equation trying to find the s. And something else. I left this a to be some constant up here. I don't know what that is. I worked through it, found out what it was in the notes, but I didn't know. I wanted to make this general, okay? I probably, when I want to try to find these guys, would like to change this, because I'm going to have to take derivatives. Every time I take a derivative, I'm going to get these a's popping down. And these a's are some kind of ugly-looking constant of some sort. They're going to make life hard. So I'm probably going to want to do a substitution here at some point, so that I can write this as e to the minus, say, y squared, where y squared is ax squared. And that way I won't have a's in my equation everywhere. So I'm probably going to want to make this type of a substitution in there just to make the math easier. That's basically all I did in a whole bunch of pages of algebra. I started with a good guess, a guess that I knew would meet the conditions. I plugged it in, I saw if it worked, and then I tried to find an equation that would solve for those f's. That's not limited to this harmonic oscillator. This can work in any physics problem. If you know something about the problem, you might be able to guess the basic form. The more you can guess about the form, the easier the equation will become. The less you can guess about the form, you may still be able to work it, but the harder the equation will be to solve. So the more you can use of your intuition, the better, because it's going to make life simple. If you don't build your intuition right now, then you're going to have to be a whole lot better at math than a lot of the rest of us. Which is why practice is an important part of doing your homework. So, I asked some questions during the thing. Could I graph some basic guesses? So let me show you what I guessed is my first set of guesses. For my wave function, my first guess is that it probably has a peak like that, and it kind of comes down like this. And if I was to look at that squared, then it'll get even a little bit humped. Oops. So it'll fall down a little faster and have a hump in the middle. Do I get the right height? No. I'm just saying it's symmetric, like we said it should be. It should be an even function. And I'm saying it should exponentially fall off, which it does. And I'm saying there should be some point that's a maximum and other places that are not. My next guess for a polynomial to multiply would be to multiply by x. Okay. If I go multiply by x, that's kind of like that. That's y equal x. So I'd expect it to go to some kind of hump. And then I expect it to go out like this. And I expect it to go down to a hump. Maybe like that. And then if you square these two, if I did that right, then didn't do what I intended. If I squared that, I would get something like maybe like that. And there'd be two humps. Notice this is very different. Here, you have a maximum probability in the center, and my guess here is you have zero probability in the center. My next guess for a polynomial would probably be something like x squared. So now we're talking about something that's kind of going like that. And so I try to do something and see what I come up with. I'm going to guess that maybe it kind of goes like this. It has three. Whoops, my fault. So I'm kind of guessing it'll have three peaks. That had one. That had two. Next order of polynomial, I expect probably to generate three. If I look at its probability, so this would be B2. B1, that's probability 1. So probability 2. And I would expect that it would look kind of like and I didn't quite get my two sides here probably right, because I expect these peaks are going to be taller than the middle peak. Why? Because of what we said earlier, that we think that classically the probability goes higher on the ends.
Why are you only guessing polynomials?
Because I just said a minute ago, based on my guess, when I sat there to make the tail and I had wiggles in the middle, that I think it should run some sort of a function that's e to the minus ax squared times a polynomial. So I started with a constant, then a line, then a y equal ax squared plus bx plus c, then the next one is ax cubed plus bx squared plus, and so forth. Now, turns out it may not be exactly that, but I expect some sort of humping thing in the middle. Okay? So these are not absolute, they're guesses of kind of what I would expect. And they kind of base on things that we've seen before. We've seen states, like with the particle of box. And the higher the n went, the higher the energy was, the more wiggles. The more wiggles, the shorter the wavelength. The shorter the wavelength, the greater the momentum. The greater the momentum, the greater the kinetic energy. The greater the kinetic energy, the greater the total energy. So I'm looking at shorter waves, shorter probabilities. I'm expecting I'm going up in energy. So I'm expecting lowest next. There are always even functions of probability. I think it's equally likely to be on the right and left. These are guesses, okay? I'll leave you the fourth one to play with the guess. Now, what's the answer? The answer is when we solve the Schrodinger equation, what do we get? So we want to know if we do the math right. So before we attack the math, which is going to be hard, we want to have a feeling for it. Now, I did a bunch of cases where I put in these guesses and I showed that they worked, and I'm not going to go through them. So I did one for the ground state where I said, hey, I'll just choose this, put in the Schrodinger equation, show that it works. And it did. It worked all the way, provided I got a specific couple of values in here. One is the value of A. The value of A to make the Schrodinger equation be true is this value. And it's always that value. So it will not fit the Schrodinger equation unless this condition is true. So you can't just put any old e to the minus 8x squared to work. This will only fit the Schrodinger equation if that A is that value. The second thing, it won't work unless the energy of the particle is that. If you put anything else in there, it doesn't fit the Schrodinger equation. So the Schrodinger equation does more than my guessing. It says my guess was good, but it also tells me what the energy is. My guess didn't do anything like that. I had no idea what the energy was. I did Schrodinger equation. I know what the energy is. It's half an h bar omega. Now that's kind of interesting. The lowest energy of a harmonic oscillator is not stationary. Yeah, I see that puzzle look. That's exactly what everybody says. What the hell? Sure, it can be set still. The spring can be uncompressed, and it can be set still, and it can have no energy. No, it cannot. If it was setting still at the origin, you would know its location exactly. And if it was setting still, you would know its kinetic energy was 0. And therefore, you would know its momentum exactly. Therefore, you have no uncertainty in momentum and no uncertainty in position, and you have violated the uncertainty principle. There's no way to have a 0-point energy of 0 in quantum mechanics. Now, that's really weird. Now, really, if you think about it, the question is how much can it be moving? How much can it be off? An atom cannot be absolutely stationary. It never can. How much can it be off? Well, it can be off by h bar, and I worked a problem like that. But I did it for a pendulum. I took a pendulum, and that's the solution of a pendulum from Physics 1, and I said, hey, if this is a quantum pendulum, it's a harmonic oscillator. If it was classical, it could look like this. You have a given length, L, and a given G, and if you pull this pendulum back and you let it go, for small deviations, no matter how much you pull it back, it will take the same time to go back and forth. You may have seen this, it's really cool. You take a whole bunch of them at different lengths and you can adjust them, and I used to pull them up and down in Physics 1 on the string and show how they would change, how fast they vibrated back and forth. So this guy has a fixed period. Therefore, he has a fixed omega. And therefore, according to quantum mechanics, he has a fixed minimum energy. Classical physics, he can be sitting right here. No potential energy, no kinetic energy, E is 0. Quantum mechanics says that's not possible. The lowest energy he can have is h bar omega over 2. So I took a 1 out of the book, and it says involve 1 second period. So that's F. And to remind you, omega is 2 pi F. So if it has a period, that's 2 pi over T. T is 1 second. So omega is 2 pi times rads per second. Multiply that by h bar, divide by 2, and you've got the energy of the minimum harmonic oscillator of that pendulum, and it's not zero, because omega is not zero, H bar is not zero. So how much is it? That. Now, that's small, but it ain't zero. It's 3.32 10 to the minus 34 joules. If you don't like that, let's do this. 1.6 by 10 to the minus 19 joules is 1 electron volt. Let's forget about all the 1.6 and 3 and so forth, whatever, okay? So that's less than 2, and that's about 3.3. You divide it by 2, you get, 1.7, 1.8 or something. 10 to the minus 34, 10 to the minus 19, that's 10 to the minus 25 electron volts. I don't even have a unit that I know of in the SI system for that small. So the pendulum is not stationary. That's a mistake. Quantum harmonic oscillator included that one. Just like the Earth going around has quantized angular momentum, this thing has quantized omega, quantized E. It's just so dang small we can't see it with our human eye. We can't measure it, but it's never zero. It can never be stationary and will define simultaneously. It's not possible.
But in this energy state, the period is still 1 second.
Period is still 1.
How,
Omega is still, because it's fixed by the length, and it doesn't matter whether you move it or not.
so how does this have a different energy state than?
Because it can have higher excited states, which are not h bar omega over 2. They're 3 h bar omega over 2, 5 h bar omega over 2, 7 h bar omega over 2. It can have higher states, but it can't have lower states. Now, obviously, the pendulum swinging back and forth has energy maybe of joules. So it's classically, pendulum is not at an n equal 1. It's at a state of like n equal 25, 10 to the 25th. Large quantum numbers, by the correspondence principles, gives us classical physics. Now, an atom vibrating can be at n equal 1. And one of the things you'll notice is that for these energies to be electron volts, this omega has to be a lot faster. So these things vibrate much, much, much faster than a pendulum does in classical physics. But my main point is, no quantum system has a ground state energy of 0 ever.
Are the excited states in this example? Are the excited states in this example basically like the angle that it's pulled through?
No, the angle it pulls through does not affect the total energy. It affects the total energy of the system in as much as you change h bar omega, NGA. So I guess in that the answer is yes.
Okay.
But you could also not pull it through an angle and give it a whack. It's the energy that really determines it.
Yeah.
The maximum angle, you mean, does it determine?
Yeah. Yeah.
So my point is, 0 point energies, kind of a misnomer. They're the minimum energy, but they're not zero in quantum problems. All right, they're not zero in quantum problems. We never had an lowest energy level in a particle in a box of 0. It can't be there. And it can't be here either. Never 0 in quantum problems. So that's one important thing to get out of this section of the chapter. There's no such thing as a 0 of a 0 point energy. It violates the uncertainty principle. The other really important thing now to get out of this thing, well, there's two. One is to get the energy levels. That's really important. And the other one is to understand how to solve problems that you don't know the answer to. So let me give you the first one. For the answer, when we're finished with all the math, there's something you should take away. You should take away an answer for the problem. One of them is you should take away what the energy value is, because you're going to need it to draw the energy diagrams. It's a very simple formula. There are a set of states whose energies go from 0, 1, 2, 3, 4, 5, 6 on up. That's their energy value. So one thing you should pull out of this section is that there's a set of levels like this. Their ends go 0, 1, 2, 3, not 1, 2, 3. They start at 0. And they're h bar omega over 2, 3 h bar omega over 2, so forth. Each one has a gap h bar omega. So you remember back in the Bohr atom, the spacing gets closer. And in the particle in the box, the spacing gets further. In this one, the spacing stays the same. So if I'm looking at a spectra, say a vibration, molecular vibration spectra for an atom, I will get a set of lines. One which is h bar omega, one which could be from here to here would be 2 times that, one could be 3 times that, one could be 4 times that, and so on. So if you get one that's 2 times that, like from here to here, you get the same answer if it goes from here to here. You get the same answer if it goes from here to here. If it drops 2 levels, you get 2 times h bar omega. So you get a bunch of evenly spaced lines in the spectrum. That's a telltale sign of a vibration spectrum.
Is that an emission?
Huh?
Is that emission spectra?
Emission spectra, or if you send light through and it's absorbed, you'll get absorption lines along the same way.
In which case they would be going up in
There'll be dark. There'll be dips, evenly spaced dips. So in your book, though we probably won't go back and spend any time on it, if you look in one of the later chapters, I believe it's chapter 10 or 11. He talks about molecular vibration in chapter 11, and he works through some spectra. Let's see if I can find some of those. I don't remember if this is the rotation spectra, but you're seeing that that's a rotation spectra, I think. See if I can find a vibration spectra. I might not be able to find it in his book. I don't see where he gave a spectra. He talks about it. We'll see it. Iceberg actually gives a picture of the spectrum. Rotation. So he's got both vibration and electronic absorption spectrum. So these things can get quite complicated in the transitions of these things. We'll get to rotation later on. These things can vibrate, they can rotate, and what you can do is you can use these things here as a way to tell you what molecule or chemical is inside of something. In fact, this is how chemistry often does their work. They take a chemical, they stick it in, take a vibrational spectrum, and from that they can tell the nature and the shape of the molecule, and they can tell what type of vibration is. So once they understand it, then they can use it as a way to identify unknown chemicals. Okay? All right, so make sure you know this. And in particular, make sure you know that the energy levels are equally spaced. Something else that's useful that you get out of the general solution, and that's the wave functions, these polynomials. These polynomials are well known. They're known as Hermite polynomials, and I work out, and I'll talk briefly about how I did it. They're coefficients, but I want to show you, I sent you a spreadsheet to play with. So in this spreadsheet, I want you to play with, you have some things that you can do. E is not, why is that not on my screen? I don't understand that. Huh, okay. For some reason my screen is not showing everything up. So see if I can move over enough where you can definitely see. It's too far. This N represents the state. So this square right here you can play with. And these two squares here you can play with, but nothing else. Okay? So if you put it 0, then it tells you what the energy is. It's 1/2 h bar omega. And it computes. If you put an even number there, you're going to put a 1 here and a 0 there. And then it will plot you the wave function. So here's the wave function. One hump, and it falls off, and it falls, sorry about that, I don't know why, it falls off over here. And if you look at the probability, I've graphed it right below, so it's even sharper. It's at 0, falls off like this. Now I didn't normalize it. I just graphed you the number of peaks. So if you have n equals 0, you have 1 peak. Let's try 2. If you have 2, you have in your probability, how many peaks? 3. How much is 3 different than 2? By 1, right? How much was 1 different than 0? By 1. If you have 4, you have 5 peaks. You always have 1 more peak than the quantum state you're in the harmonic oscillator. So if you're in the 10th state, you will have 11 maximum probability locations. The biggest ones will be at the far ends. Moving more and more like the classical distribution function I told you you'd have to do. And I've gone all the way up to 10. Feel free to add a few more if you like. I thought that 10 was plenty. All right, so there are 11 peaks in there if you count those. Each one of these wave functions is an even wave function. Meaning that if you took y equal a negative value of x, it's equal to y for the same positive value of x. Now you also can change these first two coefficients, make that a 0 and this a 1, but if you do that, this number has to be odd. So for instance, 3. If you do that, this should be an odd function. So there's at -2, so at +2, it's the negative of it. All quantum wave functions are either even parity, that's our even function, or they are odd parity. All energy states without a wave that we've ever found. They're never mixed. Now, you can have an atom that's in a mixed state. You can have 20% in one energy state and have an 80% probability of being in another energy state. But when you measure its energy, you will put it in an energy state. And at that point, it will only have either even or odd parity, never both. Right? Again, you can play with this guy and look at him, and you'll see that was 3. There's 1, 2, 3, 4 peaks. There are always 1 more peak, 1 more maximum than there are the energy state. And there's 1, 2, 3 minimums. This goes out to infinity. I don't count that as ever reaching it. So there's 1, 2, 3 minimums. The same number of minimums as the state you're in. Play with it. Make sure that you can work and answer questions, that you can graph these wave functions. Okay? You can check against my guesses on the previous thing and see how good your guess is. Now, how I got those coefficients was I did a general method that works on any differential equation that's going to be continuous, like our wave function. I said, look, it's got to be this. And I want to get rid of that A because I don't like that A. And I even know what that A should be because I solved the ground state already. So I know that that A should be this. Well, I'm going to find y so that y squared will replace that, ax squared. So if you square that, you'll get ax squared. So that looks nicer. That means that's a function of y, and I still got to find what this polynomial is. So I take that, and I plug it into the Schrodinger equation. So if you do that, you do some work on it for a little bit. Let's see if things start looking messy pretty quick. So here I plugged it in, I took its derivative, and I go, oh, look at this ugly looking thing. And I said, fine, I'll break that into parts. There's a part with phi, and then this part has a phi, but it has a y squared in front of it. And I said, oh, well, I know some things. For instance, I knew what A was. So I put in the value of A. And that's kind of nice because some things start canceling. That guy cancels that guy starts canceling, one of these, this guy starts canceling, and so forth. So I'm down to here. Still, it's kind of ugly. I said, well, heck, when I look at that, that's just A. And I can make that look like A. So I got this thing. Now, that may not impress you. I don't mind if it doesn't. It didn't impress me. But one of my problems is that this equation isn't quite finished yet, because that's y, but this is a derivative with respect to x. I need that to be a derivative with respect to y. So I take the chain rule. So there's a derivative of the function with respect to x, but I want it in terms of y. So that's the derivative of the function with respect to y and dy dx. But I know y. Y is the square root of a times x. So this is just the square root of a. And then I do it again. If I do it again, I get another square root of a. So I get an a and a second derivative. All right, fine. I'll put that in here. It's an a and a second derivative. Now the nice thing about that is that a will cancel that a, that a. So what I have now? Well, I have this stupid equation. And that's still an ugly looking equation. Where are we at over there? Okay. So I still got an ugly looking equation even after I start canceling these guys down to here. The only reason to do that was to make the equation originally have an e to the minus y squared. But I still got to solve this, and I don't know the answer necessarily by that. So what we do is we substitute our wave function in here. So I knew what it was going to look like. It's going to look like f e to the minus y squared. We said that. That's what phi is. So I substitute it. And I take its derivatives, because I don't care about the e to the minus y squared. I know about that. I want to get rid of that. So if you do that, you take the derivatives, you do that. Got two derivatives. Maybe you can do two derivatives in your head. I cannot do two derivatives in my head, so I have to do them one at a time. So I took the derivative, I took another derivative. When I do that, I get all of this junk. And I start looking at this in terms of what has derivatives and doesn't. That is the second, that has a first, this doesn't, so these two terms can be combined. That goes over here. So I put it over there. And it's got to equal what's on the right-hand side. But I noticed something. Look at this. This guy and this guy cancel each other out. I got an F and I got an F. I'll bring them all on one side if you want. Doesn't matter which way I want. But I also know something else. That has e to the minus y squared, e to the minus y squared, e to the minus y squared, e to the minus y squared. We don't need any of those. Well, of course we don't need any of those. We knew that. We were trying to find F. So I need to solve this. Good, that'll look any better. Looks pretty ugly too. All right. So you put them all together, it looks like this. And then you say, aha, I know that. In which case you're sick. Okay. The answer is yes, people do know this. This is a well-known math equation. It's in math handbooks called Hermite's differential equation. And some people then say, hey, then I therefore know the solution to that. Those are Hermite's polynomial. I do not know Hermite's polynomial or differential equation off my head. I do know the harmonic oscillator leads to it, so I know the answer because I know physics. But a person who has a lot of math would know that. When I was in math methods, I probably knew that. But what I do know is, regardless, this is a polynomial, and I can solve it by plugging in a power series. and then working through the powers. And that works even if this is not Hermite's polynomial. So what you do is you take that, a power series, and you plug it into the equation. Now, that's got a derivative. It's got a derivative and a second derivative. So I'm going to need derivatives and second derivatives of my series. Again, I told you I can't do this in my head. So I took a derivative here, and then I brought down an n and lowered to n minus 1 by polynomial. And you might say, well, doesn't that kill the n? Don't I have to change this? The answer is not really, because if it was the constant term, then the n would be 0, and that term would still go away, even though it's in the sum. So why mess with it? Leave your sum alone. Then you take another derivative. Well, you take a derivative of that, you bring the n minus 1 down. So both the n term of 0 and the 1 term go away, because if you have something like 3x, you take two derivatives, it's gone. So you have that. And now you plug those all into the differential equation. And it looks kind of nasty. All right. So that's where I'm at. I'll finish it next.